Hey everyone, we're going to move on to looking at chapter 3, which is about extreme values on an interval. So extreme values are maximum values a function takes or minimum values a function takes, and those turn out to be pretty important to our study of calculus. So let's start by looking at closed intervals. So we have a closed interval from a to b, which means the endpoints are included. And let's say we have a function that looks kind of like this. Okay, we would say that the absolute maximum of that function is f of b. So that's just, kind of, if we're looking at y values here, it's the highest point there is f of b. And the absolute minimum is f of a. So the maximum values and minimum values are y values. Now we could say the maximum, the absolute max is at x equals b. So it occurs at an x value, but the maximum value itself is a y value, f of b. Let's look at another one here, where we have something that looks like this, maybe a sort of parabolic shape, but not a very good one. All right, a and b. So it can happen that the maximum values are the same. So let's pretend these are equal. And so there's an absolute max at f of a and f of b. Sorry, not at f of a and f of b, the absolute maximum value of f of a and f of b. So they are equal to each other, and that's okay. And then the absolute minimum here would be 0. So it is 0. You could say f of 0 also, but f of 0 is pretty clearly 0 here. Okay, so that's what happens on a closed interval. Now, the maxes and mins don't have to be at endpoints. Obviously, there's one right here, but it's not uncommon for them to occur at endpoints. So endpoints are important to check. Let's say we have an open interval, a and b. So the a and b are not included in our interval. And so we have a hole at a, and we'll draw kind of the same kind of function here. A hole at b. So here there is no absolute maximum minimum value. No absolute max or min, which is sort of hard to wrap your head around unless you start thinking about limits again. So we could always get closer to whatever this whole value is. We could always get just a little bit closer. If you name a value that is really close to it, I could always name one a little bit higher, right? We could go back and forth like that forever. So there is no maximum value as we get infinitely close to whatever f of b is. And the same thing can happen at something like this. Let's say there's from a to b. We'll draw our paraboloid thing again. Let's say there's a hole at 0 too. A hole at a hole at b, and a hole at 0. And again, there's no absolute maximum minimum value there because they are not part of the graph. Those pieces of the graph where those absolute max and mins would be aren't filled in. So there's really just nothing we can say about absolute max and mins there. Okay, so let's take a look. So here's our official definition of extrema. So if f is defined on an interval containing the value c, which is an x value there. So f of c is the minimum of f if it is less than, if f of c is less than all other values for f of x, or equal to. So there could be two lowest values, what that means. So if that y value is lower than all the other ones or equal to one other one, then that is the minimum. If it is greater than all other values, then it is the maximum. So these are absolute maxes and mins. Absolute extrema, we call them. The extreme value theorem says this, says if f is continuous on a closed interval, a to b, then there exists a maximum and minimum value on a to b. So if you have a closed interval, you have to have an absolute maximum and minimum value. It could be at the endpoints, it could be somewhere in between, but it has to be somewhere. Even if you have a, the strangest case is actually a horizontal line, right? Or a vertical line, really. No, not a vertical line. Horizontal line is actually the strangest case because all the values are equal. So every value in there is both the absolute max and the absolute min, which is kind of strange. That's the extreme value thing. We're going to have, this is called an existence theorem. There are 3 of them we're going to learn in this chapter. So this is the first one. There has to be an extreme value. So we talked about absolute extrema so far, but there can be relative extrema also. So if there's an open interval containing C on which f of C is a maximum, then f has a relative maximum at C on the f of C. Let me just maybe sketch a picture to help you understand what's going on here. So let's take a look at that graph I had before. So this is an open interval. Looks something like this. So there can be relative maximums, relative minimums at points like this. This is called relative or local maximums because it is higher than every other point around it. If let's say we were just looking at a small interval like from here to here, right? Then that's a relative or local maximum. And down here we could have a relative or local minimum, right? So it's not the highest or lowest value the function takes overall. This is actually, the way I drew this, this is actually absolute max or minimum, I mean. But this relative maximum is not the highest value of the graph overall, but it is locally higher than all the other points around it. So we can have these relative extrema as well. So relative maxes and relative mins. Let's take a quick look at where some extrema can occur on an interval. And this is going to look like a lot what I just did, but let's maybe visualize it a little bit. So this is, we have A to B, and I'm going to draw a graph that looks like this. And this is a closed interval, so these are included, right? So we have, let's call this point right here C1. Let's call this point here C2, and we'll see why. So we have at C2 here, a relative max, right? Which is of a value f of C2. We have a C1, a absolute min of f of C1. At f of B, we have an absolute max. F of A is not anything here. So endpoints cannot be relative extrema. They can only be absolute extrema. So f of A is nothing. Not relative, not absolute, not special. Sorry, f of A. So nothing going on there. That is actually very interesting. Let's look at, I'm just going to maybe make a new one here. Absolute value function on a closed interval, and we'll pretend it was symmetric. On a closed interval, hopefully you can guess here that we have absolute maxes at f of A equals f of B. We have an absolute min there at f of 0, which is just 0. Absolute min value of 0. So there's a couple looks at that, and you'll see some more on your homework as you do practice problems of different absolute maxes and mins and relative maxes and mins. Let's go here. Okay, what do you notice about the derivatives of maxes and mins that don't happen at endpoints? So the derivative of the function at a max and min. Let's maybe go back right here. So what is happening with the derivative? Or in other words, what is happening with the slope? Well, right here, looks like that tangent line has no slope. Right there, that tangent line has no slope. This is only true for extrema that don't happen at endpoints. At endpoints, obviously the derivative doesn't really exist. But for non-endpoint extrema, the slope is always going to be 0. We call these places critical numbers. That's actually why I was using the letter C there before. So critical numbers happen when f prime of C is 0, or if it's not differentiable as C. If this happens, then C is a critical number of f. So extrema occur at critical numbers and endpoints. So if the derivative is 0, or if a function is not differentiable there. Let me show you an example of a function that's not differentiable real quick. You could have a function that looks like this. And so right there at 0 is a critical point, but it's a sharp point, so you can't take the derivative there. So that, but it is a critical point because that is the absolute minimum of the function. So that's what we're talking about. Okay, relative extrema can only occur at critical numbers, but not every critical number results in a relative max or min. Let's look at an example of this. An example of this would be the cubic function. Let's do the algebra real quick. So if f of x is x cubed, then f prime of x is 3x squared, right? And we say, okay, if that equals 0, we have a critical number. So we're going to say, okay, well, f prime of 0 equals 0. So there should be a max or min there, if that were true. So let's look at cubic. Okay, so here's the cube function, x cubed function, and right there is where our critical number says something should be happening. But notice it's not a max or min, it's actually right smack dab in the middle of the function, it's symmetric. So even though that is a critical number by definition, because the derivative equals 0, it is not a max or min. So we have to check our critical numbers to see if they occur in max or mins. And the way to check that is to check the slope on either side. And so we will draw some slope charts. And you sort of just draw kind of a number line here. We're looking at this is the derivative. So we thought there's a critical number at 0. And all we'll do is we'll just check some numbers left of 0 and right of 0 to see if the slope changes. This is 3x squared. So if I plug in something left of 0 to my derivative, I get positive slope. Plug in something right, I get positive slope. That's what tells you it's not a critical number if the slopes do not change. Because if we have, say, a maximum like this, right? Let's say it's at 0 again. Over here the slope is positive, and here the slope is negative. So if I get my little chart here switching signs, going from positive to negative or negative to positive, that's when I know I have a critical number. So do the same here, right? This would go from negative to positive. That's how you know you have a max or a min. All right, find the absolute extrema of f of x equals this on negative 2 to 1. So let's take the derivative. We don't need to graph these things because we know now that critical numbers are where the derivative equals 0. This is 8x cubed minus 3x squared. Let's go ahead and factor. So that's going to be x squared. It's going to be 8x minus 3. Okay, so our critical numbers, we're going to set that equal to 0 and solve. Our critical numbers will be at x equals 0 and x equals 3/8. All right, so we're going to, in our little chart here, this is here to help us out. This is x values. This is f prime of x values. And maybe I should have put these outside the box actually. X. All right, so we're going to look at 0 and 3/8. And for f prime of x here, I'm just going to put positive and negative. So here it's 0. 0, it's 0. 3/8, it's 0. So let's pick, let's try negative 1, right? Negative 1 is pretty easy. So negative 1 is going to get me a negative slope. Between 3/8 and 0, let's do like 1/4. 1/4 is going to be, let's see, that's positive. 1/4 of 8 is 2, so that's still negative. And then something bigger like 1 is going to be positive. Okay, so it looks like 0 is not a critical number. Or 0 is, sorry, it is a critical number. 0 does not have an extrema. But 3/8 is an extrema. So for 3/8, that is goes from negative slope to positive slope. So 3/8 is a minimum. Now there's a couple more places to check to find all of the absolute extrema. So we check the critical numbers, but we also need to check the endpoints to see what the values are there. So let's put in 3/8 and -2 and a 1 into our original equation to see which is the true minimum and then which of those is going to be the maximum value. So 3/8, if I factor this out, this is f of x equals x cubed 2x minus 1. Alright, so if I plug 3/8 into that, we have 2 cubed divided by 8 cubed times 6/8 minus 1. So that is f of 3/8 negative 0.013. I'm going to do f of -2, f of -2, so that's going to be a little bit easier. So that's -8 times -5, so that's 40. And then f of 1 is going to be 1 times 1 is 1. Okay. So 3/8 is our absolute minimum. Let me go ahead and change colors to write down the final answer. So we have absolute minimum of negative 0.013 and an absolute max of 40. Alright. So I know that's a lot of steps, but that is the process to get it all down. Now I think, yeah, right here I have those steps written out, so you can maybe jot these down to help you remember the process. So we want to find critical numbers first. This is when you're looking for extrema. Find the critical numbers first on the open interval. Evaluate your original function for those critical numbers. Evaluate your original function for the endpoints. And then whatever your smallest value is the minimum. Whatever your greatest value is the maximum. The absolute maximum. You could have some relative maxes and mins in there as well. Alright, we're just about done. Let's do, maybe this last one to wrap up. Find the absolute extrema of this on that interval. So we're going to start by finding the critical numbers, which is where the derivative is 0. Okay, so this is going to be 0 at x equals plus or minus square root of 5/9. Giving us some very nice numbers to work with today. Alright, so we're going to plug that back into the original function. So f of positive root 5/9 equals, let's see if I have these written down. I do. Alright, so this is 0.515. Square root of negative 5/9 is not in the interval. So be careful that you don't get tricked by that, right? Our interval only goes from 0 to 5. So we actually don't need to check the other square root. We do need to check 0 and 5 themselves, though. So f of 0 is 3, and f of 5 is 353. Okay. So our absolute minimum is at our first critical point. So this is the absolute min, and this is the absolute max. Alright. Well, if you have questions, let me know. Otherwise, I will see you in the next lesson.